Welcome! My name is Linda Strande. I am a senior scientist at SONDEC, Sanitation, Water, and Solid Waste for Development at EAVOG, the Swiss Federal Institute for Aquatic Science and Technology. I'm going to provide a brief overview of the current status of fecal sludge management treatment technologies and end products within the framework of technical tools that can be used for selecting and designing them. For more information on our research, please also visit our website. There are a range of different treatment technologies, all of which produce different treatment end products for safe disposal or end use in some form of resource recovery. Fecal sludge management is a relatively new field, so there is quite a range of experience with implementation of different technologies. There are established technologies with enough experience from implementation to make their operation fairly reliable, with existing recommendations for design and operation. These include settling tanks, drying beds, planted drying beds, co-composting, co-treatment and waste stabilization ponds, and deep row entrenchment. Hence, in the fecal sludge management book, settling tanks and drying beds each have their own chapters with more detailed information. There is another level of technology development, which includes technologies that are being transferred from wastewater treatment and other sectors, but have not yet had extensive implementation and so need more careful consideration and monitoring. These include anaerobic digestion, incineration, mechanical treatments, and lime addition. Then there are another level of technologies that are still in the innovative stage of development, but seem to be quite promising. These include vermicomposting, black soldier fly, thermal drying and pelletizing, ammonia treatment, and solar drying. And already some of the technologies on this list should be moved up to a higher level of confidence from the time when we wrote the book. For example, through our work at the Lubigi treatment plant in Kampala, Uganda, together with Makerere University, BioBurn, SEEK, and NWSC, we have shown that the BioBurn pelletizer is quite effective for reducing the drying time of fecal sludge from 60 to 90% by about half, which also translates to increased treatment plant capacity. There are also a wide range of treatment end products that these technologies produce that can be used for resource recovery. Types of end use include soil conditioner, fertilizer, reclaimed water, animal fodder, fish, protein, building materials, liquid and solid forms of fuel, and electricity. In addition to the level of experience known from implementation, it is also important to consider the treatment objectives. Technologies can then be linked together in a treatment chain depending on what the final goal of treatment is. The main treatment goals will typically first be settling for solids-liquid separation, and then depending on the end goal, dewatering, drying, stabilization, and other forms of final treatment steps such as pelletizing. This figure is taken from page 99 of the fecal sludge management book. The numbers on the diagram refer to chapters in case you want to read more about the specific technologies. So how do you select the right combinations of treatment technologies and the right treatment end products? Designing technologies for resource recovery options can define performance goals that need to be met, while increasing financial flows to offset treatment costs and provide an incentive for efficient operation of treatment plants, as operators are also providing then a product for customers. Some forms of resource recovery are shown here. You don't want to over-design treatment plants because it wastes money and resources, but you can't under-design because it does not provide adequate protection of human and environmental health. For example, if we are using dried fecal sludge as a combustion fuel in industry, we are more concerned about the level of dryness and not pathogens. However, if we are using it as a soil amendment to grow salad greens, then pathogen reduction is of utmost importance. This is the same approach engineers use to design wastewater treatment plants. You research the treatment requirement for the effluent and solids, and then you design the treatment plant to meet those requirements. This is the general definition of engineering design: the formulation of a plan to allow an engineer to build a product or infrastructure with a specified performance goal. But it seems like when designing fecal sludge treatment plants, people have forgotten about basic engineering design and do not have a way to logically select the final end goal to design the treatment plant for. Part of the reason is a combination of over-stringent requirements which cannot be met or are not enforced, and another is a lack of fecal sludge treatment requirements. Once you select performance goals, then you can design your treatment options to meet them, working backwards, considering all design variables to arrive at the solution. Design variables can be quite wide-ranging and complex, including factors such as local skills and capacities, legal requirements, regulations, norms, social acceptance, financial viability, existing fecal sludge infrastructure and services, and characteristics and quantities. You will hear more about these variables in later chapters of the book. So hopefully that all sounds logical, but how do you select the right treatment end product to design for? Especially if you're working in an area that does not have specific regulations for end use. At Sondek, we have been working on a tool together with economists and experts in business development to aid in selecting optimal treatment end products. Since the desired goal is the end use, it is important to make sure that a demand exists for that treatment product. In addition, it should be a significant and consistent demand. To determine this, we need to know the market attractiveness, which is comprised of the market size and the market growth potential. Social acceptance can be closely linked to commercial value and thus market demand. The market demand approach provides a way to identify fecal sludge treatment end products that have the largest market potential for volume and growth, and has now been field tested in Kampala, Uganda, Bignona, Senegal, and Son La, Bac Ninh, and Ba Ria, Vietnam. Through this research, we have shown that there is a higher market value for fecal sludge end products than the conventional use as a soil conditioner. A draft version of the method can be downloaded from our website. So the goal is to select an end product with a significant market, to ensure a reliable demand, and to maximize revenue. This is done by identifying currently used products in the city to see what could be replaced or supplemented with fecal sludge treatment. For example, fertilizer could be replaced by nutrient-supplemented fecal sludge pellets. Protein in fish feed could be replaced by black soldier fly larvae used in the treatment of fecal sludge. Forage plants for animals could be supplemented with plants from planted drying beds. That is just a brief overview, but you get the point. That it is using knowledge of economics, not engineering, to select end products with the greatest market potential. This information cannot be used in isolation. It then has to be factored in with other engineering knowledge and previously mentioned design variables to select the correct treatment technology options. For more information, please also refer to the planning section of the Fecal Sludge Management book. So once you have decided on your end products and your treatment technologies to produce them, then you have to know how much fecal sludge will be coming into the treatment plant and what the fecal sludge characteristics will be so that you can build it to be the right size. But the problem is there is a major gap in knowing how to reasonably estimate fecal sludge characteristics and quantities on a citywide scale or at appropriate scale for the intended area that will be served by the treatment plant. Typically, records do not exist of how many on-site systems are constructed in a city, what types of technologies there are, what quality the construction is, how often they are emptied, or if they are emptied at all. So at Sondek, we are also working on developing methods to fill this gap. For quantification, there are three basic hypotheses. First is estimating the total amount of fecal sludge that is currently being collected and transported. This is dependent on market and infrastructure and is simply a snapshot of the current situation. If a treatment plant opened today, or if there is an existing plant, this is what would be delivered. Second is based on the assumption that once you open a treatment plant and there is a legal and affordable place for trucks to discharge, then it will greatly increase the amount of fecal sludge that is being collected. Meaning, if you base your estimate on the first hypothesis, the treatment plant will already be at or over capacity when it opens. Treatment plants, hence, need to be designed to meet a capacity larger than just the current situation. But the difficulty lies in knowing what the correct capacity is. Third is estimating the total fecal sludge produced in a city, or the area the treatment plant is designed for, and is based on estimates and assumptions for populations, amount of excreta produced per capita, and degradation rates that occur in on-site containment prior to collection and transport to treatment plants. This value is how much fecal sludge would be delivered to a treatment plant if, in an ideal world, all of the fecal sludge in the area was safely collected and transported to treatment plants. So that is quantification, but characterization is also problematic due to the high variability of fecal sludge. When estimating characteristics for wastewater treatment that is continually collected and homogenized in a sewer system, it is relatively straightforward to make a sampling plan. This is greatly complicated with fecal sludge, as every on-site system has different characteristics at the household level. A sampling plan that captured the full range of characteristics on a citywide scale, or a scale appropriate to treatment plant, would be prohibitively expensive and time-consuming. To address this, we are also developing a method for characterization on the scale required to design treatment plants, based on the hypothesis that spatial demographic data can be used to design a sampling plan that will be representative but not too resource-intensive. For example, maybe income level is a predictor because on-site systems in higher income areas are potentially better constructed. We've now field tested this hypothesis with 80 samples in Hanoi and 180 in Kampala, and the results will continue to be updated on our website. So back to optimizing and selecting technologies. Another important design consideration is balancing available land with available financial resources. In general, technologies that require more land area are less expensive and less technology intensive. However, available space in urban areas is very limited and expensive, so there is a great need for reducing the required footprint of existing, transferring, and innovative technologies. To address this, Sandek is conducting research on how to reduce the required space for dewatering and drying. This can reduce the required land area for treatment or increase treatment plant capacities. Some of our recent research that has been published since the fecal sludge management book came out includes relatively simple modifications for established technologies like drying beds, such as greenhouses and mixing, which alone could reduce required treatment areas by 20%. Another possibility for transferring technologies from wastewater treatment is the use of coagulants and conditioners made from locally available waste products to increase dewatering. For example, a waste product like shells from the shrimp industry could maybe be used to manufacture chitosan. Another example is pelletizing, which, as mentioned earlier, has been proven to be an effective way to significantly increase the drying time of fecal sludge from 60 to 90% dryness for use as a fuel. More information on this research can be found on our website, and further examples are presented in Chapter 18, The Way Forward of the Fecal Sludge Management book.